Okay, so I am going to be going over an inverse Laplace transform for distinctive complex roots. So the distinctive complex roots expression that I'm going to be working with here to transform is of this form here, where you have k times e to the j theta, all of that over s plus alpha minus j beta, plus k e to the negative j theta, all of that over s plus alpha plus j beta. So in order to go from the s domain to the time domain, I will be using this transform pair that I have here, which is the inverse transform of 1 over s plus a is going to be equal to e to the negative at, and it comes from a table in the book. So the goal here is to show how this expression is fully transformed into its time domain equivalent by using the Euler equation to eliminate the complex part with j. Some people, by the way, will correct me and say that this is not Euler, it's Euler. However, due to the spelling of it, I'm going to be pronouncing it Euler. Okay, so for my Euler equations, I have e to the jx equals cosine of x plus j sine of x. Now I'm going to make a second equation, which is e to the negative jx equals cosine negative x plus j sine negative x. That's just by making the argument here for x, making that negative. So that's my second equation. So when I take the first equation and I add it to the second equation, I have this expression here, which is e to the jx plus e to the negative jx equals cosine of negative x plus cosine of x plus j sine of x plus j sine of negative x. So next, let's take note of the fact that cosine is an even function. So anytime I have cosine of negative x, the equivalent of that is just simply cosine x. So next, let's take notice of the fact that sine is an odd function. That means sine of negative x equals negative sine of x. And so when you use these expressions here within this relation here, this equation here, then what you have is e to the jx plus e to the negative jx equals 2 cosine x. This all simplifies to this when we apply this. Okay, so this is going to be used as a link between a complex expression in the time domain and then also a non-complex expression also in the time domain. Okay, so to start off with the equation, we have here, number one, we have k e to the j theta over s plus alpha minus j beta plus k e to the negative j theta over s plus alpha plus j beta. So just take notice here again that you're in the s domain and you do have a complex part here to it. Okay, so next what I'm doing here is I've extracted from the numerator in both sides of this. I extracted the numerator here as well as here, and then we have this expression, which is k e to the j theta times 1 over s plus alpha minus j beta plus k e to the negative j theta times 1 over s plus alpha plus j beta. Next, I'm going to apply this inverse transform here, and so wherever I see 1 over s plus a, I'm going to relate that as being a e to the negative at in the time domain. So here, this whole expression here, alpha minus j beta, is going to be your equivalent of what a is here in this expression here. Okay, so once you substitute and you use that there, then you can get this expression here, which is k times e to the j theta times e to the negative t times alpha minus j beta. That's where your a is at. And you're going to have this plus k e to the negative j theta times e to the negative t times alpha plus j beta. Okay, so next we're going to expand this. We're going to multiply inward and expand this expression, and then what we end up with is k times e to the j theta times e to the negative alpha t times e to the j beta t plus k times e to the negative j theta times e to the negative alpha t times e to the negative j beta t. Okay, so next I factor out k times e to the negative alpha t, and then I'm left with this expression inside these parentheses here, which is e to the j theta times e to the j beta t plus e to the negative j theta times e to the negative j beta t. So next I simplify even a little bit more, and I end up with k times e to the negative alpha t, and then in parentheses I'm multiplying that by e to the j times beta t plus theta plus e to the negative j times beta t plus theta. So at this point, what you want to take notice of is that it is in fact in the time domain because we applied the inverse Laplace transform to it, and it is in the time domain. However, because of the imaginary unit there, j, we have complex parts to this, and it's a lot more convenient to have it without the complex parts. So using the expression that I derived a couple of slides back, I'm going to use e to the jx plus e to the negative jx equals 2 cosine of x in place of what we have here. So the substitution is going to be that x equals beta times t plus theta. When we apply that substitution, then we end up with our final expression, which is k times e to the negative alpha t times 2 cosine of beta times t plus theta. And so we can further simplify that a little bit more, but just by putting it in a more standardized form. And so we end up with 2 times k times e to the negative alpha t times cosine of beta times t plus theta. All of that is equal to the inverse Laplace transform of this expression here, which is what we started out with, which is k times e to the j theta divided by s plus alpha minus j beta plus k e to the negative j theta divided by s plus alpha plus j times beta. So this is your final expression here, your final equation for a transform pair. And so this completes the scope of what I did want to go over here. So anytime you see this expression here and you need to inverse Laplace transform it, then you can just use this expression here, and that is it. So hopefully this was helpful for you. Thank you for watching, and have a nice day.